Hello everyone, welcome back to online lecture series on fluid mechanics and hydraulic machines. We are continuing with our topic of dimensional and model analysis. In our previous lecture, we have completed till the Buckingham's pi theorem and we also took one example for the same. Now let's move forward with our new topic. The topic is model analysis. So first we will define what is model. It is a small replica of actual machine or construction, actual machine or structure. Then prototype. It is the actual machine or structure. Then the next definition is model analysis. It is nothing but study of such models. Now let us define the next term, that is similitude. A similarity between model and prototype in every aspect. So what is the meaning of this? That model and prototype. Okay, again I have made a mistake. Typo. So they both have a similitude, means a similarity between model and its prototype in every aspect, or that means that model and prototype both possess similar properties or both are exactly similar to each other. Now there are three types of similarities. Let us define the first similarity. First is geometric similarity. So as the name suggests, the model and prototype both will have similarity in terms of geometric aspects. So here the ratio of corresponding linear dimensions in model and prototype are same. So let's have some nomenclature here. LM is equal to length of model, then DM diameter of model, and VN being volume of model. So similar kind of properties or dimensions can be written for prototype: LP, DP and VP. Okay, so here okay, few more dimensions are there, that is BM is equal to breadth of model, and AM being area of model. So here we can also add BP and AP. So here LP upon LM is equal to DP upon BM is equal to BP upon BM is equal to LR, where LR is what? Scale ratio. Then we can also write down for area ratio, that is AP upon AM is equal to LP into dP divided by Lm into Vm. So that is going to be Lr square. We can also write down for the volume ratio, that is Vp upon Vm is equal to Lp upon Lm cube, or it can also be written as Vp upon Vm cube is equal to dP upon dm cube. So that is going to be Lr cube. Now let's move forward to the next similarity, that is kinematic similarity. So it is similarity of motion between model and prototype. So what is the meaning of motion? That here the velocity ratio and acceleration ratio will be same between model and prototype. So here let me write down that ratio of velocity and acceleration at corresponding points in model and prototype are same. So I will not be spending much time on nomenclature part. So here so let us say Vp1 is the velocity of prototype at its point 1, and Vm1, that is the velocity of model at corresponding point 1, which will be equal to velocity of prototype at corresponding point 2 divided by velocity of model at corresponding point 2, that is equal to, we can write down Vr. So this will be equal to velocity ratio. Similarly, we can write down the same for acceleration, that acceleration in prototype at point number 1 divided by acceleration in model at point number 1 is equal to acceleration on prototype at point number 2 divided by acceleration of model at point number 2 is equal to AR, that will be equal to the acceleration ratio Now let's move forward to the third similarity over here, that is dynamic similarity. So here the meaning of dynamic similarity will be ratio of corresponding forces at corresponding point between model and prototype are same. So here we can write down for inertia force, that is inertia force in prototype and inertia force in model is equal to, let us say we define for, also we take viscous force, so Fv of P divided by Fv of M is equal to, we can also take gravitational forces, so Fv, so Fg of P to Fg of P is equal to same. So this is known as Fr, that is equal to force ratio. So let's copy this work into our main slides. Let's move forward with our next topic. That is types of forces acting on a moving fluid. So first is inertia force. Which is equal to Fi, which is equal to nothing but mass into acceleration of the mass of the fluid into acceleration of the fluid. So it will be m into a, and the direction of inertia force will be in the direction of the acceleration of the fluid. Second is viscous force. That is Fv, that will be equal to the shear stress multiplied by surface area As. Third will be gravitational force. Or gravity force simply, which will be equal to Fg, and it is written as mg. Fourth one is pressure force. Pressure force Fp is given by P into A. The next is surface tension force, fifth one. Fs, which is equal to sigma, that is surface tension into length. Then sixth one and last is elastic force. Fe, which is given by elastic stress into area. So we can say it as TB into area. So these are the forces acting on a moving fluid. Now let's move forward with our next topic. That is dimensionless numbers. So first is Reynolds number, which is equal to Re inertia force upon viscous force. So here first we will see inertia force Fi, which is equal to m into a. So it can be written as rho into v stands for volume multiplied by acceleration, that is velocity, upon time. Here we can put density into volume into velocity divided by time. So what we will do is we will combine these two. Volume upon time gives us the flow rate, and if you recall, Q is equal to A into V, where V is velocity here. So we can write down rho A V into V. So finally we are getting rho A V square, that is the value of Fi. Then we require the viscous force. So Fv is equal to tau into area, where tau is viscous stress or shear stress, which is equal to mu into Vu upon Vy into A. So here it can be written as mu V A upon L. So this is the value of Fv. So now Re is equal to rho A V square upon mu V A upon L. So V will get cancelled, A will get cancelled, so we are left with rho V L upon mu, that is the value of Re. So that is the Reynolds number. And also this is the end of today's lecture. Thank you for watching this video.